quick review of the rewriting stuff we talked about. So the first two with this log here are essentially the same thing. Only thing you need to remember is when you don't see a number written down here with log, a little number underneath, the base of that log is 10. It's called the common log. It's also the one you'd see if you had a calculator in front of you, or if you go to Desmos and you go to plug it in, it just says log. It's using this common base 10 log, okay? If there's a little number written down there, it becomes the base of your power when you write the other way. So this one down here with 10, this is called the common log. This one here where they change this to this ln, this has base e. This is the natural log, okay? This is natural log is used because if you think back to our growth, natural log, because this is continuous growth. Natural log is used to solve continuous growth. Log is used to solve for any of the other bases, okay? And then the common log of 10 is because back when we first made this, we only had one of them available on our calculator. We had to pick something that we could easily convert to, and it was base 10. But I want to actually talk about what log is doing here. So if we have b to the x equals a, well, I'm just rewriting this the other way, and we transform that into log. This is log of base b of a, something we plug into our calculator, and it outputs an answer. The answer it outputs is x. And what I really want you to see is that x is the exponent. The reason we use log is because log isolates the exponent. Thus, it allows us to plug in and find what that exponent should be. Meaning if that was a variable, we could actually solve for it if we could plug that log into the calculator. The beginning practice of this was going through and just rewriting some stuff. So if we put these things in log form, now one thing to remember when you do this, I have this written with words up here. Base to the power equals the answer in exponential form. Log, and this is not written great, but this should be subscript slightly below the main line. Log of whatever the base was of the answer equals the power. And the key thing I remember is when I write log from exponential form, the power is always by itself. That's the important part. So we're going to write these in log form. The x is by itself because the x is the power, and the power is always what ends up by itself. Now I'm going to have to put the word log in here, and this log is going to have a base of 3 because it's also the base of the exponent. That's the reason it's called the base of the log. And you're going to write it as a little number down here, and then the only thing that's left is that answer part from our exponential. That 27 gets written right in here. Only thing that changes with the second one, and this one can be confusing because we always want to put the x by itself, even though we know the answer to this, but we're just practicing rewriting here. The 5 is the exponent. It's by itself over here. The number we pulled the exponent off of is the little number with log, and then whatever was out here becomes our x. I mean, becomes the answer part of that. That's where x goes. Opposite direction. So remember, this part is your exponent. The little number with log was its base. So this is x squared, and that means that should be 100. Right in here, we can go 3 to the 4th. Should have been x. And what you can see, especially with these bottom two, what you had to do with a lot of our assignment from Monday, you can find x by rewriting these quite often. Like we know that when we have x squared equals 100, we know that's 10 because that happens to come out to one that we know that we're comfortable with. 3 to the 4th, we could plug into the calculator. It's going to be 81. It would tell you x is 81 if it asked us to solve these things. In the very beginning, though, we're really just working on rewriting these things from one form to the other that kind of leads us into some of the basic solving. Because I want to say you guys did, well, hold on. You guys did most of the Delta Math assignment had you rewriting to solve, right? Which is kind of all in the same step, but there was all ones that you could essentially guess, or you got the answer by plugging in once you rewrote it, like the bottom two, okay? We can also do this with natural log. Natural log just gets a base of E, and remember, E is that constant for continuous growth. That was that 2.71 number, but even more. This is a button on our calculator in Desmos when we need to use it to evaluate it, okay? So let's just write this in exponential form. Now, this natural log, one thing to remember, when you see natural log, you could rewrite this as log with an E down here. And you can do the same thing we did on the other slide. So this one is log E5 equals 1.61. Which means in exponential form, this is e to the 1.61 is 5. That's what I'm asking you to do here. You don't have to rewrite it every time, but sometimes it's helpful in the beginning to remember that there is a base down there. Same thing with these. If we ever get one, it says the log of 7 equals 10. Let's not use 10. Equals 15. And we're missing the number down here. If the number is ever not written on the normal word log, the base of this thing is 10. If it's ever not written, the number that should be down there is a 10, which makes this 10 to the 15th equals 7, which doesn't work because I just made it up off the top of my head instead of making one that works. So don't try to plug that in. It doesn't actually work, but I just want to focus on where the numbers rewrite from. I probably should have made this an X. It would have made it work, made it look a little bit better. Anyways, so this is e to the 0.262 equals 1.3. And part of the reason I do these with all numbers, if you took your calculator and you plugged in e to the 1.61, you would get really close to 5. It's rounded. If you plugged in e to the 0.262, you would get really close to that 1.3 that I have listed as the answer for that exponential, okay? Kind of prove to you that it works. Logarithmic form. I see a lot of people struggle with this one because it's written backwards from the way that we've seen it in the notes. This is the base and the power. This is what would be considered the answer. So this is log. The e goes down here. Remember, it's equal to whatever the power is. The power is y. The e goes down here because the e was the base of that power, and we put a 9 in here. But you'd be expected to write that with the natural log because it's a log base e. So the same thing is going to happen here. We're going to get a base e and r to the t. Even if there's more than one power, whatever's in the power always goes out as its answer. And 2 was what we had here, and we'd be expected to simplify that into that for our final answer. This one's interesting, and this one will pay dividends when we go to solve, but I actually want to plug that in and see what I get. So I'm going to jump over here to Desmos. And remember, that e to the power button is over here in functions. ln, natural log, is also a function. So we wanted to know what the answer to natural log of e was. Now, what was the power of e if there's nothing written? Every number technically has a power. There's nothing written on it. That power should be a 1 because 1s don't change anything. So just put a 1 in there. Whoops. 1 in there. And the answer that we get is 1. Doesn't seem really useful yet, but it's important to understand that the natural log of e is going to be 1 because what happens here, natural log is a log with a base of e. This is e to the 1. You could solve these without a calculator. Anytime the base of your log matches the base of your exponent inside, all of this stuff cancels, and this is your answer. Meaning, if I wanted to know what the answer of, let's take the natural log of e to the 5th. What should that equal? Well, this is log base e. This is e to the 5th. So again, we see this matches this. So then our answer for this is only going to be this power every single time. And that'll work for any log where you make the base of the power mass the base of the thing inside the parentheses. And we could check that over at Delta Math. I'm sorry, not Delta Math, Desmos. We put a 5 in there. You can see right over here we get a 5 as well, okay? So that's one property that will become useful as we work through and we start the solving that we're going to talk about today. So we use these things to try to solve problems like this. Because this has a log in it, and we first look at it, this is a little bit scary. You get one like this, the first thing you should do is rewrite this as an exponent. That's 4 to the 3rd equals x. So just by rewriting our log as in its exponential form, we isolated the x. And now we could easily plug in 4 to the 3rd and figure out what our answer is. So that means it's 4 to the 3rd, which gives us, I've got it covered up, 64. So the answer to this problem is 64. And that's where I believe a lot of your Delta Math work was at. It had you rewriting to solve. Same thing with this one. This is a base 10. So this is 10 to the 2.5 equals x, which we can plug in and we can solve. So 10 to the 2.5, 2.r, but 2.5. And that gives us 316.2277. Maybe round to 2 places would be fine. So 316.23. So this is about equal to 316.23 would be adequate for our answers. And the last one that I have for us gets a little bit more complex, but not anything crazy. So we're going to rewrite this in exponential form. 2 to the 5th equals 3x. But I don't want 3x, I want just x. So follow your normal algebra here. To get rid of this 3, we're going to divide. So that gives me 2 to the 5th over 3. That's something that I can plug straight into the calculator. So let's do that. So we're going to go 2 to the 5th. And we're going to divide that by 3. Oops, I hit the wrong button. And I got 10.6. Now, one thing cool with this, you see this little button right here, it says it'll convert it to fraction. That means that this has a fraction form that you might need to see as well. It means you won't have to round. It says it's 32 thirds. So 10.6 forever or 32 thirds. So let's say this is 32 thirds or it was 10.6 forever. And really that comes down to when you're using that calculator, if you're answering a question on a quiz for that, you're gonna have to kind of match it up and make sure it's in there right, okay? Because it may say don't round, so that means you have to use the fraction. So that's where most of our stuff lied yesterday. Now there's a couple additional things to do with this, okay? Because I had you work with problems like this, where we're solving for exponents. That's really where we want to head. We want to be able to solve for exponents. Now, with these first two, did you need anything special to solve for? Now, you could probably guess those, right? 2 to the 4th, 2 to the 5th. Which one equal to 32? 2 to the 6th. So you could guess and check those is what I'm getting at. You could say, well, what is, I think it looks like it might be 2 to the 5th. That's 32, so it's not 2 to the 5th, so that means it's got to be 2 to the 6th. That one gave me 64. That's what we were looking for, wasn't it? No, it was 2 to the 5th. So I could guess and check this one to find it 2 to the 5th. I know 10 to some power will give me 1,000. I know that that one is 3. I could guess and check that one. If we come over here and look at this one's a little bit tougher, but you don't need any logs or anything to solve this one. What power would you use to turn 5 into a 25? That's a square. So we know right now, well, that x has to be 2, but there's something special about it, because what you have to remember with this is that when you have negative exponents, it puts that number in the denominator. It's a formula. It's a property that you learned a long time ago. So that one will be x to the 2. That's probably one of the hardest ones on guess and check. This is where we want to work to, because I have 1.04 to the 2. And most of the time, if we do guess and check, we would try whole numbers, maybe even some fractions. You're going to spend a long time trying to guess and check this one. This type of problem, to solve for this, we need log 4. Now when we go to do this, let's write this in its log form and see what happens. So we get x out here. That's what we wanted, because remember, log allows us to solve for this. Now it gives us a base of 1.04, and the number inside is 2. So I need to figure out how to plug in that log of 1.04 over 2. So let's head back to Desmos. Now notice Desmos just has a log key. It doesn't have anything for me to plug a number into. So anything that just has a log key like this is log base 10, and that's not the log that I wanted. So there has to be a way to rewrite this thing so that I can use that key, and there is. There's a property called the change of base, okay? And what it's going to allow us to do is it's going to allow us to solve for this one. And we just get this simple log of a different base. You're actually going to get 2 logs out of this, and they're both going to be base 10, ones that we can plug into our calculator. And the way that I remember this is I remember there's a number that's lower and there's a number that's higher, meaning not value-wise, but actual height. This one is written higher up than the 1.4. The 1.4 looked like it was, the 1.04 looked like it was on the bottom. That one goes on the bottom. The 2 goes on the top, and that change of base, where I write this as 2 logs, gives me something that I can plug into the calculator to actually solve for these, okay? So I can come back over here and I can go log of 2. Now you have to be very, very careful when you plug this in, because there's a reason that I put parentheses around those numbers. Because you have to, whatever number you want inside there, you have to close the parentheses around it before you do anything else, okay? So I have log of 2. I want to close those parentheses and then hit divide and then do log of 1.04. Now it'll tell me my answer, 17.67, okay? And I'm going to write that down. So it tells me that this power should be 17.67. If you had tried to guess that, I just don't think that you would have made it to that number very easily. And you can prove that what we've done just works by actually plugging this back in. If I go to Desmos and I plug in 1.04, and now I know its power to the 17.67, let's look at what it equals. If we solve this problem correctly, it should be 2 or really, really, really close to 2. So let's go back and do this. So it was 1.04 to the power of 17.67. And you can see here we get 1.999765. It's not exactly 2 because we had to round this answer a little bit when we wrote it down, but it's pretty close. It's close enough to understand that it's rounded. That's why it's not exactly 2. So you can check that one. So the way that you solve these ones that you can't guess and check, write them in log form, and then change the base. That works for a lot of these simple ones, okay? Now there are a couple other things that we're going to have to talk about to deal with log, because as some of these get a little bit more complex, doing this a little bit differently helps, okay? So let's talk about a log equation that has log on both sides. So this is new for us. If you ever come across a log equation that has one log written on either side, and notice that it's the same base, meaning there's a log 2 here and a log 2 here. There's a log 3 here and a log 3 here. If this ever happens, you can cancel those out. Now it only works if there's just one of them on either side. If you have more than one, you'd have to do something else. But then to solve this expression, you would just need x equals 2x minus 4 to figure out what x is. And you can solve this now. So let's see, if we subtract that, we get negative x is negative 4. So x is going to be 4 for this problem. And you usually end up with either a linear or this one will give us a quadratic. 7x equals x squared plus 12. If you ever get a squared with it, it's a quadratic, you're going to have two answers. You need to make sure that you set this equal to 0. Move everything to one side. So I minus the 7x over here. And then you need to factor this with the box to find the answers. So we get x squared, we get 12. And we want the factors of 12 that add to negative 7. So that's going to be negative 4x and negative 3x. So this has a negative 4 and x and a negative 3. So that thing factors into x minus 3, x minus 4. And then the last step, you're going to get two answers. Each one of these parts gives you an answer. So what makes x minus 3 equal to 0? When x is 3 by adding it over, and that's one answer. The second answer, so you put a little and in between them, is when x minus 4 is equal to 0. So we get another answer of 4. When you're solving these type of equations, just make sure that you plug them back in. You don't get a negative inside the log. You can't take log of a negative number. So you may encounter some of those. We're not going to spend a ton of time on those because I don't think you'll see most of those. And really the important part of this, what we're working towards, is we want to be able to solve these problems. Now I'm going to show you the same process in two different manners. One like we did on the previous slide. When you have one that's set up really easy and you just want to solve for an exponent just the way that it is, you can always rewrite this as a log because that puts your exponent by itself. The base becomes the base of the log, and the 64 is what we want to take log of. We can't plug that into the calculator, but by change of base, we can do log of the top number divided by log of the bottom number, and that will tell us x. That we just need to go into the calculator and plug in. So log 64 over log of 4. So we have log 64 divided by log of 4. And we got an answer of 3. Which is one, that was also one that we could have guessed and checked, but I wanted to solve it that way. We know that 3 works. And we can do the same thing with this second one. If we work through that problem, and I'm going to do this one two different ways because I want to show you when we get to some of the more difficult problems, the change of base, in my opinion, becomes a little bit tougher. We're going to learn a different way to apply this that I think works a little bit better. But if we did this with the change of base, we would get log base 9 of 3 equals x, meaning that our x can be found with log of 3 divided by log of 9, which is going to be 1/2. I promise. So we can do it that way. There's also another way, because really the change of base formula is a shortcut. It's a shortcut for doing what I'm about to do. The other way you can deal with this, and this will pay dividends with some of the more difficult problems, I think. We can apply log like it's an operation. So I can write log on either side of this thing. The reason I do that is there's a special property of log that tells me that any power can be written as a multiplication in front of that. So I get x times the log of 9 equals the log of 3. And then I can divide that over, and look, we have what we just did with that change of base formula by rewriting. And we're also going to get 1/2. It's just a slightly different way to look at what we're doing, okay? Different representations and different paths to solve problems sometimes can help you a little bit more, okay? I think we'll be fine for most of them with change of base, but it might not be bad to practice this way. And on top of that, a lot of the videos you've seen, anything you may search out on your own, will most likely solve them this way and not with change of base, because it's a little bit more powerful, a little bit more versatile, okay? Let's try this last one. So this one's different because I've got a power that's got different stuff with it. But let's do a change of base first. So I'm going to write this as a logarithm. And that means that 2x minus 1 becomes the answer. The 3 is the base. And the 27 is what I want to take log of. Now, I can find this answer by using the change of base formula. And I can plug the log 3 over log 27 over log 3 into my calculator and find its answer, as long as I plug it in correctly. And I see log 27 divided by the log of 3 is 3. So now I have an exact answer. I'm going to write that in. So that means this is 3. Can we solve for x now? Easily. We could add the 1. So 3 plus 1 is 4. Then we could divide this, and we'd end up with 2. We could easily check this, because is 3 2 times 2 minus 1, is that really equal to 27? So we could always go back in and plug in our answer into the power and make sure it works. So let's actually plug it in and see that it works. So we're going to go 3 to the power of, it was 2 times 2 minus 1. And there it is. You see we get exact 27 because we're the exact answer here. And that worked perfect. You could solve this just like I did with the other one. It's a few more steps, but what you've got to be really cautious with here is you may need to carry some stuff, some decimals in your calculator before you get there, because this division right here isn't always going to be a whole number. And that could make things a little bit messy as you get towards the end. So let's do one more. Let's say we want 4 to the 2x minus 1 equals 27. And let's do this the same way. So we're going to go log, and we're going to have base 4 here, and it's equal to 2x minus 1, and this is the 27. So this stuff is over here. We're going to go log 27 divided by log of 4. Now when we did this prior, we got a nice pretty number to write down that made our math easy, okay? We come and do this now. We're going to go log of 27. We're going to divide that by the log of 4. Is that a nice number? No. And really what happens here is you really don't want to round this until the very end, because logs usually give you smaller numbers, and if you round poorly in the beginning, it's going to affect, especially when you're plugging things in on a computer, to match your answer at the end. So when you get one like this, what I suggest, since this number wasn't pretty, let's just write this down, knowing that we have to plug this into the calculator and figure out what I need to do after I find that number. Meaning I had 3 and I added the 1. So what I have here is I have this log 27 log of 4. And I know I can find that number. I'm just going to plug it in the calculator and find it. But what I need to do is I need to move these 2 steps over so I can figure out what to do with that number in the calculator afterwards. So I'm going to add the 1, and then I would divide the 2 to find the x, right? What we're doing is we're saying I'm going to find this in the calculator first, and then I'm going to go answer plus 1, answer divided by 2, so that I don't have to round until the very end of this thing, okay? We're trying to preserve accuracy until the end. So we have log of 27, and I'm not sure if it works on this. It does. If you type in ANS in Desmos Scientific, it'll bring up your previous answer. And what did we want to do to that? We wanted to add 1 to it. So let's go plus 1 and hit enter, and it added 1 to it. And then we'll do the same thing. We're going to type in ANS, and it brings up the previous answer. And we wanted to divide 2. We're going to divide 2. And we see that that should be 1.69. Sometimes it won't matter, sometimes it will. And I know you guys have seen plugging numbers into the computer for quizzes and things can be tricky and spotty sometimes. But it's also one of our standards of math is that you preserve accuracy until the very end. And sometimes that means we've got to be cautious with how we plug things into the calculator. So 1.69 is what we'll write down for our answer. So this is 1.69. And again, we could plug it back in and we could test it and try it that way, okay?